So this question asks a hypothetical. How many quadratic functions can I find that passes through the point -5, 0, 10, 0, and 0, -1? Right? If there indeed exists any such function, quadratic function at all. So we marked those 3 points, and then we've been playing around with some sliders in Desmos. Actually, the first question I want to ask is, what are these sliders doing to the graph of this quadratic function?
So C.
Let's start with C.
C changes the x, where it applies on the x-axis. The y-axis.
Y-axis. So C is kind of what is it doing? How is it moving the graph here? It's just, it's sliding it directly up and down. Hang on to that observation for section 1.9 in a few weeks, because that's going to be one of our key tools when you talk about graph transformations, is how do I just move a graph without changing its shape? How can I move it up and down? Well, I can do that just by adding or subtracting a number on the end of its formula. In this case, the C is playing the role of that vertical shift, is what we're going to call it in section 9 of this chapter. So that's what C does. What about A? A does look like it's changing a slope somehow. If I take a large value of A, what would we say about the slopes of this parabola? Notice I'm saying slopes.
A shrinks it.
It looks like it
narrows
it narrows it. It looks like it's just it pushes it inward towards its axis of symmetry, which here is the y-axis right now. Right, so it kind of makes it narrower. Another way to think about it, by the way, instead of thinking about making it narrower, we could also think about stretching it upward vertically. For a parabola, it turns out that those two are exactly the same thing. Other shapes, we might get different results if we stretch it vertically versus squish it horizontally. But that, too, is another type of graph transformation we're going to talk about at the end of this chapter. What else can A do?
A can invert, too, if it's
can.
negative.
Right. So as soon as my A values become negative, now what has happened to my parabola? It's inverted. It's facing downward instead of upward. In calculus, you're going to call the difference between these two the difference between a function which is concave down, that's what we would call a parabola like this, and a function which is concave up, as we would call this one. There's one other possibility, by the way. Not concave up, not concave down.
Linear.
Yeah, what happens? How do I make this linear?
0.
If A is 0. Because then what happens to the formula for this quadratic?
It's just linear, you know.
I gotta try and get there. It's just like
It makes it
exactly. It turns it into the y equals mx plus b, right? Because this whole term would be gone, and we would just have f of x equals bx plus c. That's the equation of a linear function. Exactly. So I can't quite get my mouse to work here, but if we made a exactly 0, like that, there we go. Now we would have a linear function instead of quadratic, which is neither concave up nor concave down, because its slopes are the same everywhere. And in fact, whether a function is concave up or concave down is a measurement of how its rates of change are changing, whether they are increasing or whether they are decreasing. Okay, so that, by the way, what about B? Did anyone have a good explanation for what B is doing? It's easier to see if we...
Changes like the angle of its, or I don't know, how would you call that?
Notice as I change B without changing A or C, how is this shape moving?
It's almost like it's moving in a parabola.
Yeah, it's like it's moving in a little parabolic trajectory. That would be an interesting little research question, right? Is it true that as I vary the value of B, that the location of this parabola itself moves along a parabolic trajectory? I actually don't know the answer to that off the top of my head. It'd be a great research question. Great. So the B is a little more complicated, but A and C, I think it's clearer to see what those are doing. So what do we think about this question in the activity? Is there a quadratic function, and if so, how many, that passes through all 3 of these points? For a second. One way of answering this question is just to try to freehand it, right? If I could draw a parabola between these 3 points, what would it look like? And the point that you made was that at least we know that if such a parabola exists, it's going to be concave up, right? Because the point in between these two is beneath the 2 of them. And so whatever parabola might exist has got to sort of face upwards. This is a very crude drawing here, so, pay no attention to my artistic skills. Okay, so that at least sort of plausibly that there's a U shape I could draw that passes through these 3 points. Tyler, your observation is you thought that there was only one such U-shape. Why is that? So the claim is that this formula would actually work, right? Let's just try typing it in, right? So if I take and make A equal to 0.02, you said, right?
Mhm.
And B was negative 0.1,
Yep.
right
C.
there. C is negative 1. There we go. I have my graph hidden for the moment. Let's re-enable it. Hey! Look at that.
Oh, you know what it is too? Look at where that.
So we discovered that, in fact, yes, these values of the parameter do give me a parabola that passes through all three of those points. And, moreover, you just said that negative 1, the value of C, happens to show up on my graph where?
At the y-intercept.
At the y-intercept. So let's think again about why that should be true. So here is my value of C. Negative 1 also happens to be my y-intercept. Why should I expect that my y-intercept of this function happens exactly at the y-coordinate C?
Well,
That's what it represents.
Because that's, well, yes, but why is what I'm asking, right? How do I know? So what does y-intercept mean again? Like, how do we know when we're at a y-intercept or we're at the y-axis? The value of x is 0 at a y-intercept. So do the thought experiment. What happens if I stuff a 0 into x in this function? A times x squared is going to become a times 0 squared. It's gone. B times 0 is going to become
0.
right. But C is still C. It's whatever it is, right? In this case, negative 1. So of course, when I plug a 0 into this function, everything except for that C is just going to vanish. And so the C must then be the y-coordinate of my y-intercept. Right? So that C is always our y-intercept, necessarily. And as we previously talked about, the fact that my A is positive means that I indeed do have the concave up opening parabola that you were talking about, Jake. But I also want to talk about that lowest point question that you brought up, because this is the other piece of what we're being asked to think about in this whole activity, of which I encourage you to do the rest of it at home, because there's a lot of good stuff there. But where is the lowest point, roughly? Where is the lowest point of this parabola?
Maybe 1.1.
Yeah, it's a little bit lower than negative 1, right? One of the things we can do in Desmos is we can try just clicking on that point, because very often Desmos will sort of label these control points for us, like things like the vertex. By the way, we call that the vertex of a parabola. Either its lowest point if it's concave up, or its highest point if it's concave down. Right? And so it looks like that's the lowest point. So here's the question that I want to leave us with for further investigation. So this is, as you look back at this activity, rewatch this video. What I want to know is, how could we get information like this to show up in the formula? Because these numbers for A, B, and C don't seem like...
They're not arbitrary.
They're not arbitrary. There's definitely a relationship, right?
Yeah.
Because once I pick an A, B, and a C, I actually get one, and only one, quadratic, one parabola, right? And that parabola is going to have a vertex. And so A, B, and C will determine the vertex, but it's not clear from this how that happens. And so here's my observation. We're going to want to be flexible enough to understand the same parabola in 3 different algebraic disguises. The first one is this disguise, which is called the standard form, right? Where A, B, and C are playing the roles that they play here. So 0.02 times x squared plus negative 0.1, so minus 0.1, x minus 1. So that's the standard form for this parabola. The second form that we want to be able to use is called the vertex form. And as the name suggests, this is a form which is going to tell us what the vertex of this parabola is. And I'm just going to write this down without proof. So I encourage you to check me. I'll tell you how to check me in a minute. But vertex form would look something like this. Minus 1.125. Okay? So why is this called vertex form? What am I seeing in this equation? Remembering that the vertex is this point, right? The beauty of vertex form is that the coordinates of the vertex jump right out at us. The x-coordinate, 2.5, is sitting right here. And the y-coordinate of the vertex, negative 1.125, that's looking at me right here. Right? So there's benefit to that. But the vertex form doesn't show me what the y-intercept is anymore, right? The negative 1 information that we got out of here, we can't see the y-intercept now. Right? So each of these forms has its advantages and also has its disadvantages. Right? It reveals one set of features of my parabola, and it obscures another set of features. So that's why knowing how to use all of them is helpful. Here's a third form. As you might expect from the name, the factored form is going to be our way of rewriting this thing using a factorization. Oh gosh, so I've got to think now about how this is supposed to work. So here is a factored form for this quadratic. What information is the factored form telling me that the other two forms didn't? The x-intercepts. Exactly. It's telling me the x-intercepts. -5 is one of my x-intercepts, and that would seem to correspond to this number here, +5. Right? +10 seems to correspond to the other one. +10 turns into a -10 over here. So let's, just to wrap this up, why should the factored form tell me the x-intercepts? How do I find the coordinates of the x-intercepts of any function? We did this once with the disappearing ice cap. How would I do it with this function? At x-intercepts, the value of y is equal to 0, right? Y is 0 at this point. Y is 0 at that point. So how would I use that information to enable me to use algebra to find these values? Where would I put that 0? I would put it in here at f of x, exactly. After all, that is what the meaning of graph is. The graph of a function is the set of all points in the xy plane where the y coordinate is equal to f applied to the x coordinate. I mean, that when you say the word graph, it has that specific meaning in our course. And so y and f of x mean the same thing. So if I want the x-intercepts, I want to set y equal to 0 and then solve for x. And so what's going to happen, this is our throwback to our algebra workshop now. How would I solve this for x? Well, let me start by multiplying both sides by 50 to cancel out this 0.02. Right? Divide by 0.02 if you like. That's going to get rid of that, but the left-hand side is going to be 0 divided by 0.02, so it stays 0. So now how do I solve this? Right, so we talked about in the algebra workshop that when you have a factored polynomial on one side of an equation, and a 0 on the other side, so that 0 is all important, right? That was the mistake that I made that you all caught, right? We can break it apart into two equations, each one set equal to 0, and then solve each one of the equations, which is much simpler. And that's why the signs change here, because now I'm going to have to subtract 5 from both sides. X equals -5. That's my first x-intercept on this side. And then when I add 10 to both sides of this one, x equals 10, that gives me the other x-intercept. Right? So one of the things to get accustomed to is just being able to kind of translate between the kinds of information that each of these three forms can give you, and then also practice the algebra that it will take to get from one of those into the other.